Hello, welcome to Maths with EJD. In this video, we talk about the SciPy.Interpolate module. Not to forget, SciPy is actually scientific Python, and it's powerful. It has a lot of functions for doing technical computation in science and in engineering and all those areas. Um, like you already know, all the notes I'm using here have them stored up on Google Drive, and I put the link in the description box so you can click on it and then access the notes and open them, especially if you already have Jupyter Notebook installed. Or, I mean, you can open it by clicking on it in Google Drive. You probably can just open it straight up on Google Drive. I mean, on Google Colab, rather, without having to worry about Jupyter Notebook, even because Jupyter Notebook and Google Colab function about the same way. So with that, you can actually follow me and try whatever I'm doing hands on. And of course, my formula for learning coding is you code by coding. Just try it. When you run a code and it works, tweak it, change some values, see the impact it has. So as you see those changes, it begins to register in your head how all of this thing go about. And of course, you don't want to miss any of this thing. This is like the 17th video in the whole scientific computing with Python series. And I have so many more to come. So you don't want to miss any of this. So if you have not subscribed to this channel, you want to surely do that. And of course, you also want to hit the notification bell so you can always get alerted each time a new video is released. Of course, keep your comments coming. Tell me what you like me to talk about, whether in maths or or using Python, right? Of course, you want to comment, you want to like, you want to share with other people who these things can actually be useful for. All right, the SciPy interpolate module. So the SciPy.Interpolate module in Python provides several functions for interpolation and smoothing of data. You know, sometimes you have data and it can be quite rough. So interpolation is what helps you to make sure whatever missing points are there in the middle are actually smoothened out. All right. So you can actually use interpolation as a kind of method for supplying missing data. You know, missing data is a big problem for data scientists or data analysts, and there are many methods to actually take care of them. Interpolation is one of those methods, and that's why we are checking that out right now. So let's go. First thing, let's talk about interpolation functions. And there are two of those. We are considering two of those interpolation functions. We are considering interpolation in one dimensional, in one dimension, and interpolation in two dimensions. That's interp 1D and interp 2D. So interp 1D actually performs linear interpolation for one-dimensional data, and it constructs an interpolation function based on input data points. So the whole idea of interpolation is you have some data, and then some points are missing. So what interpolation does for you is to fix those values that are missing so that you can, if you're plotting it in a curve, this curve can be smoother. Okay, so let me put the line number so I can refer to lines easily. Show line numbers. Okay. All right. So of course we know we are talking about SciPy.Interpolate because we want to talk about interpolate, and interp 1D, that's interpolation in one dimension. And of course we need numpy along the line, and because we need something like sine and linspace, they can only come, they are functions from numpy. All right. And then of course we need matplotlib.pyplot, which you're going to talk about later, though. But because we need this, you won't enjoy interpolation if you don't see things being visualized. That's why it's like we are getting ahead of ourselves to talk about some data visualization methods. I'm going to talk about matplotlib and Seaborn after down the line, actually. Okay, so here we have x and y. All right, we have x and y, and x and y. The value x is from 0 to 10, and it is in 10 equal divisions, meaning that we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 specific divisions like that. You know, combining those 10 points, right? I mean, it's not a bad idea, but it is, if you divide 10 into 10, that is not as smooth as when you divide 10 into 100. That is why the interpolation we are doing now in line 8, we now have a function, we call it interp 1D x, y. So we want to interpolate in one dimension, x, comma y. So the new x now is now 0 to 10 in 100 divisions. So 100 divisions means that between 0 and 10, there are 100 points. So that way, if you plot a curve with 10 points and you plot another one with 100 points, of course, the one with 100 points is going to be smoother, right? And of course, we know interpolation, that's part of the job it does. So you can now say that your new y now will now be the function, the interpolation function with your x new, all right? And then, so we can plot it, because if we don't plot it, you won't really appreciate what is happening here. So the first plot is actually of the original data with 10 points, sine x plotted with the values of x from 1 to 10, just 10 points, and that is represented using O, and that's the original data. And of course, x new and y new, that's the interpolated data. So you have, of course, your legends to show whether it's original or interpolated data, and then you show all that. So if I run this, it takes a bit of time, and then it spews out the result. So you can see this. Okay. So the original data is just 10 points like this. So the interpolated data now takes care to be sure that, so it can now join up something like this. Now imagine if I make it into like 100, if I make this number 100 into 1000, you're going to get a smoother line, all right? What if I make it into, say, 10,000? The line also becomes smoother. Okay. I mean, well, of course, it's not looking as remarkable as should be, but I mean, that's generally the idea of interpolation. Now you're going to see some better smoothing as we go on. All right. So, but the interpolation is that you can now join those points up and be sure you're doing something right. Okay. So let's talk about two-dimensional interpolation, interp 2D. So, and this is used for two-dimensional interpolation. That means you have X, Y, and Z, right? So you have it like you're talking about cuboids, cubes, and things like that, three-dimensional stuff. Okay. So it can perform linear or cubic interpolation depending on the method specified. So again, the normal NumPy, SciPy.Interpolate, and now we are importing interp 2D, not interp 1D like we did before. Of course, we need to visualize with matplotlib. So here, you declare x from 0 to 4 divided into 5 equal divisions, y 0 to 4 divided in 5 equal divisions, and then you have the z randomly generated, in 5 divisions, from 0 to 5 in 5 equal divisions. So, and then in line 10 and 11, of course, line 11 is creating an interpolation function, which is interp 2D x, y, z. So kind can be linear. So there are other methods like linear, cubic, and quintic. So I'm going to try that out. So after the first one, I'm going to change linear to, say, cubic, and then you see how that works, depending on what you need. So you now need to define the new grid points for interpolation. So x new is NP line space 0 to 4. Instead of 5 now, you have 100. I mean, for the old x's were in 5 divisions. Now you're going to have them in 100 divisions, so that making them smoother. So that z new is now a function of the new x and the new y, right? Of course, integrated, because of course, f is for two-dimensional interpolation. So all this now is to plot you're plotting the results. So this is for the original data. Since it is three-dimensional, it's better to split them apart, because you're going to have something that looks solid, and then you have the interpolated data in another place. So you can see the transition taking place. If I run this, what do we get? Okay, so you can see here, you can see remarkable data points like that, showing solidly. But from the interpolated data, things are a bit smoothened out like that. Things are a bit smoothened out. So let's do the experiment like I did before and say, instead of 100, these are now like 1000 each. So things become even smoother, most likely. Yeah, maybe a bit smoother like that. So the number of divisions is what does the job right here, as you can see. Okay, so let's talk about proper smoothing functions now. The other time we're talking about interpolation functions. So these are now smoothing functions. And one of those would be univariate spline, and then there's smooth bivariate spline. Those are the two we are considering here. There may be more, but these are the two we are considering in this situation. So the univariate spline fits a spline to one-dimensional data, providing a smooth representation. Okay, of course, from SciPy.Interpolate, we have a function called univariate spline, and of course we need NumPy and matplotlib.pyplot like that. And of course you have your x, which is -3 to 3 in 50 divisions, and then y is defined as e raised power minus x squared plus 0.1, and that is plus some random things, happening right there, of course. So you now in line 8, you have a variable named SPL for spline. So univariate spline X comma Y. So you're doing univariate spline X comma Y. So XS is now NP lin space from -3 to 3 in 1000 points instead of the 50 before. And then if you represent this now, XY R0, MS is 5, and then you have XS this with the spline together. So these are like the new stuff. So you see how things smoothing out pretty much. Okay. So the original data is -3 to 3, right? So you have data in -3 to 3, that just 50 random points like this. But then with the spline thing, so you get a smooth curve that fairly represents all the data points. That's the basic idea right here. Okay. So let's move on to smooth bivariate spline, which provides a smooth interpolation of a two-dimensional data set using a bivariate spline. So here things are more a bit more complicated, a bit more advanced. I think that's a better word to use. So of course, we now get a smooth bivariate spline from the SciPy.Interpolate module, and then we have generates random input. So we have the random seed of 0. And now this is important for reproducibility, such that each time you run it, you keep getting the same result. So it doesn't keep changing. So sometimes if you are working with random numbers and you don't want them to ever change, so you can use your random seed, which is a function inside of NumPy, to guarantee that whatever you have will always be what you get as far as you don't change anything. Because normally random stuff are supposed to change. So you generate your X, which is 100 random values, your Y, another 100 random values, and then Z now is defined as the sign of XY, the sign of 10XY, so to speak. So that's an example function scaled for more variation, right? So that's it. Create this smooth bivariate spline. So you see the procedure is always the same, starting from interp 1D, right? So where you want to declare that, you say F is equal to interp 1D XY. Here it's smooth bivariate spline XYZ, like that. So the keyword is smooth bivariate spline with SB and S all in capital. Pay attention to that. So this SPL is just a variable name representing what's happening here, and this is where the real job is happening. And then you now have your X new in 100 divisions like before. So but instead of it's from 0 to 1 in 100 divisions, 0 to 1 in 100 divisions. So the X new grid, Y new grid is now np.mesh grid of X new, Y new, because things are going two-dimensional now. So that Z new is now SPL X new, Y new. And then, of course, you have all this talking about the representation. Let's see what that gives us. Okay. So you see, you have all this data now. And then when you interpolate, see what it looks like. It now becomes something smoothened out this way. Of course, still trying to follow the shape of the data as much as possible, right? So this is like a rough estimation of what you actually have right here. Okay. So let's look at other utilities for SciPy.Interpolate module. Okay. So other utilities talk about grid data, for instance, which interpolates scattered data points to a regular grid. Again, we follow the same kind of idea like before. So you have sin XY, sin 10XY, so to speak, like that. And of course, we generate this random stuff. So then you are defining the grid for interpolation. So you have XI, which is equal to YI, and that is 0 to 1. So this is guaranteeing like a square. You have square on both sides because it's from 0 to 1 for both Xi and Yi. And then XY, YI again is on a mesh grid covering Xi, Yi. So you have a one square unit like that. Okay, so the interpolate using grid data now will now be Zi is now grid data X comma Y put together, and then you have Z, and then you have Xi, Yi, and the method. Oh, the other time I promised you I was going to change. The first time we came about, here, this linear, we could also do cubic. I just remember that now. So if we do make it cubic, see what it is like linear. But if we do cubic now, which I've changed, the kind now is cubic. If I change that, see what you get. So probably it's smoother than that. To tell you, we have you have linear, cubic, quintic. Cubic is degree 3. Quintic is degree 4, right? We don't have that kind of thing here. So, but here we have it again. So talking about grid data now, and the method is linear in this case. So trying to run that, see what the kind of thing you get. So what if we try to make it, I don't know if cubic works here. Let me check it. Does cubic work? Cubic, because here it's method not kind. Okay, cubic also works. Does it necessarily look better? I'm not sure. We need a bit more check to be sure of that. And it can be quintic, that's order 4. Quintic, order 4. Does that work? Okay, that doesn't work. Okay, good. So let's stay with our linear and move on. So we can do linear and cubic in this case. Linear. Okay, so that goes. Nice. All right. So let's talk about SPLEV and SPLREP. So this evaluate B-spline basis functions and their derivatives, right? Or find the B-spline representation of set of data points respectively. Okay, so here you're of course importing SPL REP and SPL EV like that. Of course, you're generating the data point X now from 0 to 10 in 10 divisions, and of course you're doing that for sign X. So to create the B-spline representation, so you just have some TCK, that's a variable name for SPL rep XY. Then here you're creating the B-spline, and next thing is to evaluate the B-spline at new points. That's where the SPL EV thing comes in. So you now have X new is from 0 to 10 in 900 divisions instead of 10. So Y new is SPLEV, X new, comma TCK, like you have. And then, of course, you have all this whole thing to represent them graphically so you can appreciate what's happening. So you can see how smooth this whole thing is. We start with 10 points, but now the spline thing is really smooth, from 0 to 10, like that. So you may want to consider this if you need something smoother than Interp 1D that we did previously. Now let's talk about some advanced interpolation methods like rect bivariate spline. So which provides a two-dimensional spline representation for gridded data. It supports both linear and cubic interpolation. So it supports both linear and cubic interpolation. Let me bring this down. Say this is some bullets, and then this is another one, so that this goes like this. Yeah. All right. So here we have one more thing. So we now have mpl underscore toolkit.mplot3d axis 3D. So we are going three-dimensional now because we're talking about rectangular bivariate spline, which is under advanced interpolation methods. So here now we have x, that's minus 5 to 5, 20 divisions. Y, minus 5 to 5 in 20 divisions also. X, Y is now, so we do that on the mesh grid. So Z itself is like this sign of the square root of x squared plus y squared, like that. And then, so to define the final grid for plotting the surface now, you have x fine, minus 5 to 5, 100 divisions. Instead of 20, you now have it final in 100 divisions. Then y also is in 100 divisions. So x fine, y fine, over the mesh grid, x fine, y fine, like that. And then, of course, you come to 17, 18, 19, where you actually do the spline thing. So perform spline interpolation on the original grid. So the spline is interpolate rect bivariate spline XYZ. So Z interpolated is spline X fine, Y fine, grid true. So plotting, so to plot it now, you use all of these things. So, I mean, when we get to data visualization, we can focus a bit more on this aspect. But for now, we need to see, because if you don't see it, you won't really appreciate. Now you can see the original Z values are this, they are a bit rough. But then when you come to the interpolated surface, things are a bit smoother. Things get smoothened out better than what you have in the original Z values, right? So we also have some additional utilities and methods. Let's talk about radial basis function, for instance, which performs radial basis function interpolation for multidimensional scattered data. All right. So here, again, you have all those 100 values generated, and you're looking for sign XY like that. And then the random basis function RBFI, which is really happening in line 13, is RBF XYZ. And then the generate grid point for visualization. So you have X new instead of before it's just 100, right? So again, you have 0, 1 in 100, 0, 1 in 100, and you have that over the mesh grid, and you have all this for visualization. And then if you run that, see what you get. Okay, you get something this smooth, like that. Something this smooth. Okay, so that's RBF interpolation of Z equals sign X multiplied by Y. Okay, so let's look at LSQ univariate spline, LSQ univariate spline, which fits a spline to one-dimensional data using least squares minimization. So this uses least squares minimization so that, okay, here you have, of course, now it is LSQ univariate spline that we are importing from SciPy.Interpolate module. So the data again is from 0 to 10 in 10 divisions. And then, of course, we are doing that. So we are using this to generate sine x. So to fit the spline, we have the variable name SPL, and then this is where the real work is done in line 10. LSQ univariate spline XY with T is 2468, even numbers following like that. And then the next thing, you try to visualize the data to see what it looks like. All right. So it gives you something really close to that Interp 1D, So you have all these options to check how these things actually depend on what you want, right? So here we have practical applications. For instance, interpolation, you can actually use interpolation for image processing, and I find that very interesting. So some image processing can begin to start from here, even before you go into the whole idea of computer vision and stuff like that. All right. So interpolation for image processing. So it can be used to upsample or enhance resolution in image processing tasks. So I mean the code becomes a bit lengthier because you are dealing with pictures, Now here I'm trying to interpolate one of my pictures. Let me see if I can show you that picture. Yes, it's on the desktop. Inside scientific computing. Yes, let me show. Yeah, this is the picture. Look at the picture. This is the original picture, right? Why is it opening here? No, I don't like this. No, okay. Let's open it properly. Let's open it properly with say open with photos. Yeah, open with photos. Yeah, so this is the original picture. So in fact, this one was generated from the code. So let me delete this now so that you can see that I'll come back here later. So you see, by the time I run the code, it would have worked on this picture and generate that picture. So let me close this now. I'll close this. So by the time the code is run, I'll come back here to show you that the job is done. So see what's happening here. Here I'm loading an image. It's actually that picture I just showed you. So I load the image in line 6. So I say image equals PLT. So we need matplotlib to load the image. plt.imread dansu underscore 2 JPEG. You can see the picture again. See, let me go back. Probably I should just have minimized. Okay, scientific computing. So see the picture dansu underscore 2. So this is the picture opened. Now it's going to open in Canva again. I don't want that. Open in photos, right? Open in photos. So this is it. So and the name of the picture is dansu underscore 2. That's it. That's the name of the picture. All right. So let me just minimize it because I'm coming there later. So once I run the code, you see what we get. All right. So the picture is loaded. So it is that is loaded as into my image now. So so the next thing, we set the image shape, the height, the width, and the channels. That is done in line 10. So the image shape gives us the dimensions of the image. So it tells us the height, the width, and the channels of the picture. And then in line 12, we create arrays of X and Y coordinates corresponding to the image dimension. So once we get the dimension here, so we now have X, which gives the range of the width of the picture, Y, which gives the range of the height of the picture. So this is like X coordinate from 0 to width minus 1, Y coordinate from 0 to height minus 1. So if it's like, if the height is like, say 40 centimeters, so to speak, I'm just thinking. So 40 centimeters, right? So that's like you move from 0 to 39 because counting in Python start from 0 like that. Okay, so the same goes for height. So the next thing is we extract one channel of the image, e.g. the first channel, which is the 0th index. You can choose any channel depending on the image and what you want to achieve. So, I mean, you can play with this and see the different results. So if you're really interested in working with pictures, right, you can check this out a lot. So the image channel, we just pick the 0, assuming we are working with the first channel. So you can go to second channel 1, third channel 2, and things like that. And then you can create the interpolate function using interp 2D. So we are using interpolate 2D now. So So X, Y, the image channel, and the kind is cubic. Maybe I'll come back and try linear later and see what that looks like. All right. So then you say define new X and Y coordinates for the interpolated image. So that image now so the real work, the interpolation work is happening in line 21. So now we are doubling the resolution of the image, right? As you're going to see. So X new, so it is two-dimensional, right? Because we're working with a picture. So X new now is, from 0 to the width minus 1. Then the width is multiplied by 2, and the height is also multiplied by 2, like that. So you have X new, Y new, like that. And then you come to line 29 where you integrate all of that together. So the interpolated image is now interp function X new, Y new together, like that. And then the rest is something to plot. So plotting the original and interpolated images side by side now. So you have axis 1, axis 2. So plot two subplots. So the original picture and the interpolated picture will be shown together. So the first one is the original image, the second one is the interpolated image. So lines 47 to 49 talks about, so that's me saving it as interpolated image. So as you're going to see there, it's going to show as interpolated image, and it is going to show in grayscale. That's like black and white. So, and then it will tell me that interpolated image has been saved as whatever the output file interpolated image. So that's going to take a bit of time because it's a picture we are working on. So let me click that and let's wait for some time. So it's running already, as you can see up here. When you see that star, it means that the cell is running. All right. So it's going to take a bit of time because we're working on the picture. So once the result is out, it is going to generate the two pictures below that cell. So let's wait for some time. So at this point, I think it's a good time to tell you, if you have not subscribed to this channel, please be sure to subscribe and of course share with other people because you have a whole lot to learn here. And don't forget to hit the notification bell so that anytime I upload a new video, you can see it. So you can see what has happened to this picture, and see what has happened to the picture. It has been rendered in grayscale, and that's what we have, like that. So let me see. This is now, if you go into the folder now, because I've saved it, you can see the picture has come. This is now, no. I keep forgetting to open it in another format. So let me open it with, say, photos. So you can see that is what the code, the interpolation did on the picture. And I think I really love this. I love this. Okay, so that goes. So now I want to tweak the code and see what happens. So we did cubic before. Let's do linear and see what happens. Linear. So let's see how much we have to wait a bit because we're working with a picture. So, I mean, this can actually be your introduction to maybe computer vision or working with images using. So you can see that all the matrices, all the statistics you learn in school, they actually have their use. So in fact, all these computer vision, working with pictures, all of these things, they're actually matrices at the core. Now you can see, I guess there's a bit of difference. But I'm not sure. Except if we're able to compare the two side by side before. So, I mean, in fact, let me copy this code out. This is linear now. Let me go and do cubic and let's see how they compare with themselves, right? So I put this now. Instead of linear, I come cubic. Then I run. Of course, it's running already. When you see this, it's already running. And then let's see what happens with the picture. Let's see what happens with the picture now that it is cubic, or at least let's compare them side by side. So that takes a bit of time because it's some serious task that is being done. Let's see how that pans out. Hoping for that to come out in a bit. Yeah, that's it. So okay, it's like the tie color here is darker for linear than for cubic, if my eyes are not deceiving me. In fact, let me okay, I think this is what I should do. So this is saved as interpolate image. Let me save this as 2 so we can see the two together. Let me save this as 1 so we can see the two pictures together inside the folder. This is 1 now. So I'll rerun each of them. So I run this now. So it's running. That's the one for linear now. So I'm saving it as interpolate image underscore 1 so that we can see both of them in the folder. So we can see, compare them side by side and see what exactly we get. So I mean, coding, if this is your entry point into Python, I think it's a very nice place. Okay, so this one is out now. That it has been saved as interpolate image 1. Okay, so let me do the second one, which is interpolate image 2. Interpolate image 2. Let's see what that gives, and then we can go back and check. In fact, I think I want to change the CMAP to something and see what it looks like after now. So you can, if you have time, you can begin to experiment with all of this and see how interesting these things are. Really, really interesting indeed. So it should come out in 1, 2, 3. Good. 1, 2, 3. So that's so you have the picture. Now let's go into the folder and look at the two of them. So see the two pictures generated. Okay. I think there are some differences. Oh, I keep forgetting this. I think there's a bit of difference. The first image seems darker. Oh, okay, this one has been here before. Okay, I guess I need to delete this so we can just see. Yeah, good. So we can see this. So image 1 is a bit lighter than image 2. This is linear now, this is cubic. So it means that, I mean, that depending on the kind of scale you want. So I keep forgetting. Let me open with photos. Open with photos. All right. Okay, look at this and then look at this. Yeah, this is brighter, this is darker. Interesting. So linear is lighter and cubic is darker. Linear is brighter, cubic is darker. Right. So that's cool. All right. So I still want to try something. Let me try something. Let me try something. Let me try something. What's that now? Okay. Yes. I'm looking at the CMAP. I want to change it to something. Let's see if it works. Though I'm not very sure how well that works. Okay. So let's do this. There's a particular color map I like. I don't know if it's available here. I just want to change it to, let's say, rainbow. I think there's a color map like that. I hope it's here. If it's not, no problem. Just want to try it out. And this is how you learn coding, right? You just keep trying things out, and then I want it brighter, which is linear in this case. Well, I don't know what's now that the color has changed. Maybe it can be error. I'm not sure. I just want to check it and see how well that works. The mistake I've made again. I should change it to like image 3 because this now is going to overwrite what I have before. That means I have to run that again. Of course, no problem. We are learning. So let's see how fast this comes in 1, 2, 3, 4. Aha. Okay, now I see what's happening here. So I see what's happening here. Like that. Interesting. Wow, this is really interesting. So that's image 2 now. So let me take back to this. All right. This, like this, and we have say, okay, let me take it back to gray. Gray, and I won't forget to change the name. Gray. Gray. And I call that image 3. So this comes down. Okay, the first is cubic. Okay, cubic. Okay, cubic is lighter actually. Linear is darker, I think. Right. Let's say 1, 2, 3, 4, 5. Okay. So we have all that now. So in the file, you're going to see all of that. So look at all the, so what computing is doing to all of this now. Okay, so that's about that. So we have one more thing under scientific, under Interpolate, and that's about another application which is in, so the first application is in, say, what is it now? Oh, okay. I've gone very far because I was experimenting. I mean, you can keep tweaking this code to get different things. So you have practical application, interpolation for image processing. Another thing is time series data interpolation, time series. So you can actually interpolate time series. You have a time series data. That's it. When you hear time series data, it actually means you have sequential date and you have some values. Basically, that's what that's about. So in this case, what I'm using a particular data set, which is also here. So I'm using a data set I call time series, and it contains some data like that. So it's some dates in 1979 to say what's that now? Say 1985 or something. Yeah, say 1985. Yeah. So you can, now the interesting thing is that you can see some values and then some other missing values are in between. So the job of interpolation is to make up for every data that is missing in between like that. All right. So like that. Okay, so that's the data set we're working on for that last cell. So if you come back here now, you see I have, so because I'm working with data now, I need to use pandas. Pandas is the library for data manipulation, data analysis, and all of these things. So, and of course, we need to visualize in this case. Okay, so this is time series data interpolation, right? So it's like I have veered off course. I've gone to talk about, okay, here we still used SciPy.Interpolate, right? So here I'm using pandas. So I mean, maybe just take that as some Jara, I mean some extra on what I'm doing. So in line 5, this is where I upload that data. So it's the data is called time series and it's an Excel file. So that's XLSX, that's the ending. It could have been a CSV file too, or any of these other formats. Then the date is converted into a format that works best for data analysis. And then we need we need numeric column. We need those things to be numbers. And then of course here the interpolation is linear, so we have that here. So the rest is just to visualize. If I run this now, so you see that data set comes like that, shows all the points, and then so you can see it goes like that. So I want to experiment and change the method to say cubic and see what happens. Let's say cubic and see what happens. Okay, in fact, now this data set down here that you have, okay, in fact, let me do something. Let's say, instead of just saying print all that, I'll just say print. In fact, I'll just say df interpolated alone. So it will show us all the data, like that. I just say df interpolated instead of saying print. So you can see it's showing us even any part that is missing now, it will show us everything, right? It will show us. So everything that was missing before, you can see that it is all, it has all been taken care of. For instance, okay, if we go back to the data set, right? Let's say I go back to the data set. I know that, okay, you can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 values are there. 11, no value. Then 12, 12, 13. Okay, of course, this is 0. So 0, from 0 to say 10, there's data. 11, no data. Then from 25, there's no data again, from 25 to like 30 something. So let me visualize the first 50 so you can see, you now see that there's data everywhere now because we have interpolated. So let's say data.head, data.head, and I do the top 50. So you can see normally the top 50, not every data should be available. So now you can see the top 50, they all have values. So you can see everything has value. Or let's pick a date where data is missing so you can understand better. Say 1979, 1126, no data. But now 1979, 1126, there's now data for that. So you can see everything now has data. All the 50 have data now. And that's the job of interpolation. And that is linear. So here I want to make it cubic and see what exactly happens. cubic. All right, cubic. So I just run this and see what happens. Okay, so I mean, that is actually smoother. That is smoother. I did simlog. Let me silence the simlog and see what happens here. Okay, so it's the kind of thing that is happening here. So some very beautiful stuff. And of course, the data points are actually replaced like that. So data points actually replaced. So, I mean, this is a very good way to actually interpolate missing data. And of course, it's particularly useful for the kind of research I currently do because I work with data a lot these days. So we've come to the end of this. It's so interesting. You don't want to play with this. So, you know, just practice, see how all of these things work, and you'll really be glad you did. So see you on the next video where we'll talk about another SciPy module. Probably that should be optimized, I'm not sure. All right, so if you have not subscribed, be sure to do that. Hit the notification bell so that you can always get alerted, and comment, like, and share. Thanks for always stopping by. See you.